Hello everyone. After recording the CCing process on a GT-40 head combustion chamber last week, I'm left with a lot more questions than answers. That chamber measured out at 65.8 cubic centimeters, which was surprising, because I was expecting it to be in the 60 to 63 cc range. I expect that the other chambers in these heads will have close to the same volume. But after doing some compression ratio calculations based on what I knew, it became clear I need to know more about these heads. Even if I were to overbore the block with flat top pistons, these heads will develop pathetic compression if I leave them as they are. I'm going to show you the numbers, but for me, if I'm considering drastically shaving these heads, I need to know exactly what their current dimensions are before making any changes. So in this video, I'm CCing the remaining combustion chambers and carefully considering what needs to be done before I cut a good set of heads into something that might become useless in the future. I'm using red food coloring for this go around. It would help to close this before I start filling it. I filled it up about 2 cc's above the zero mark, so I'm going to have to drain some out. On the money. So I don't know if these valves are going to hold the water or not. I guess time will tell, because I didn't remove them and clean them and check the seat myself. I just left them in, brushed out the chambers so there wouldn't be full of carbon. The spark plug is in the hole, so it won't drain out there. And I actually drilled 2 more holes in this same plate, so now I can set it up and do 2 neighboring chambers without lifting the plate. Okay, I think we're ready to go. Let's see what happens. When this air pocket is full of red water, it'll be ready to take a reading. And it's taking its sweet time, that's for sure. But that's okay. That's it. I could actually see a little bit of that fluid starting to come up inside the vent. So if you remember, the first one I checked was 65.8 cc's or milliliters, however you want to say it. This is about 67. Yikes. 67.3, I would say, milliliters. 67.3 cc's. Wow. Okay, I've got to reset the Burette and move it over to this one. I'm going to go with it. Okay, so I moved the spark plug to that one, and it's time to take a reading. The plexiglass, and I started losing water out there before this air pocket here was gone. So, oh, look at that. it filled back in. The water bubble that was sitting on top here, when that air left, the water got sucked back in. That's amazing. There's still a little bit of air right here. I'm just going to give it a little more. Whoop, that was too much. Okay, so there's a little water bubble there, but if you remember, I started just a tad below a full 100 milliliters. So that might just make up for that error. This is like 67.4 cubic centimeters is what I'm reading there. Crazy. Okay, time to reset and do the last one on this head. So I reset it and I set it up so that I can take another reading on this chamber, and this is the last chamber on the head. I'll read that one too. But this time I clamped everything down so I have a nice even seal around the edges, and hopefully we'll see a slightly different reading. We'll know for sure when I redo that one. The only problem here is it's too difficult to get to this valve now. Let me see. Rotate the whole thing. There. Okay, here we go. The spark plug is in the hole. I blew these out. There's no water left in either one of them. That's as close to perfect as I can get it, I think. And let's see. That's about 65 point, guess what, 65.7? About 65.7, 65.8 really. Just like the first one. All right, let me recheck the third one. So I just refilled the second chamber again, this time with the polycarbonate sheet clamped down. And I'm reading 66.6 cubic centimeters. Okay, so this is chamber number 3 as I've been doing them. I set it up to remeasure again with the clamps on the plate. So let's see how this goes. The spark plug's in there. I don't expect anything to be leaking. So I think another lesson I learned is that yellow is better than red. I could see better with yellow. Okay, that's it. It's about perfect. So it looks like 66.1 or 2. 66.1 or 66.2. I guess I'll say 2. Although it's not quite there. So using the clamps across the board, I got better readings. It makes sense. I think that using the grease as a seal, you need to really compress it, or it holds the plexiglass up off the head a little bit. So the results are in on this first head. This chamber is 65.8 cubic centimeters. This one is 66.2. This one is 66.6 cubic centimeters. And this one is 65.8 cubic centimeters. The total variance between all of them is 0.8 cubic centimeters, so they're less than 1 cubic centimeter difference across all of them. The spec that I saw said these should be 60 to 63 cubic centimeters. So if you go by the 60 cubic centimeters as the spec, this chamber here is 66.6, so it's 6.6 cubic centimeters larger than would be ideal. Now, these heads can be shaved a little more probably and reduce the size of those chambers, which I'm almost certainly going to have done. But how much should we shave off these heads now? They've already had one little shave. The guy that sold them to me said they were minimally shaved just to flatten them out. And there's a rule of thumb floating around out there that 4 thousandths shaved off the head will reduce the volume by 1 cubic centimeter. So if you were to take 20, that would be 5 cubic centimeters reduction. The 289 heads are advertised to be 55.6 cubic centimeters at the most. I'm not going to be able to get all the way down there, but I would like these to be below 60. I did some calculations on the compression ratio, and anything I can get below 60 would help a lot. Shaving these heads could get it from 9.5 to 1 compression ratio to 10 to 1. But I need them to be below 60 cc's volume in the chambers for that to happen. So that rule of thumb says 4 thousandths shaved would reduce it by 1. That means shaving them 20 thousandths would reduce it by 5 cubic centimeters, and 30 thousandths would reduce it by 7.5. If I could do 7.5, that would be great. That would get it down below 60 on the biggest chamber, because that's 66.6. So if I could reduce it by 7.5, that would be really good. It would be 59 basically. And down in that territory, the compression is really good. The compression ratio that I calculated would be really good. So how do we determine how accurate that rule of thumb is? So I figured out an experiment I want to try that will tell me for sure if it works. It'll reduce the chamber size by 7.5 cubic centimeters, and that would put it right where I want it. The other question is it still safe to take 30 thousandths off these heads? And that's a question for the machine shop. They know better than I do, but I'm venturing a guess that it's still good to take 30 thousandths off these heads. So I'm starting this process by cleaning the head surface. I need to make sure there's no grease around this chamber. That's going to help me with the next step. Boy, I got that stuff all over. So this stuff is plastic shim stock. It comes in various sheets, and these packages usually come from like this one here is 1/2 thousandths thickness. I have almost no use for that. Then 1 thousandths, then 1.5, then 3, or 2 and 3 and 4 and 5, all the way up to 30 thousandths, which is coral. Unfortunately, they're color coded, so coral is 30 thousandths. Unfortunately, I don't have any coral left. And I don't have the key on here anymore either, so I don't know what yellow is. I'll clean it off better in a second, but so measuring it with a micrometer, that's 20 thousandths dead on. And then pink, Pink is 15. So that would be too much to use with the yellow. What about black? Black is 12.5 thousandths. And I have just a little bit of brown left, but I think this is just what I need. Yep, that's 10 thousandths. So the idea is, what if I could cut a 30 thousandths thick shim stock that would fit perfectly in that dimension around the top of the, really the bottom of the combustion chamber here. First I would have to figure out how to mark it and then cut it. I'm thinking maybe, and this is just an experiment, I have to experiment before I can do the experiment. Yeah, that clearly shows the line there. I could have tapped on these edges a little more to make them show up better. But this is just to get the idea of what can be done. Okay, so that should be the shape of the combustion chamber. It's very close, not perfect. I didn't expect it to be. And when I go to do, I'm going to try this with the shims. I don't know if they'll mark so easily. That's close. But anyway, you get the idea of what I'm trying to do. I'm going to make 30 thousandths shim stock that will just fit across the top of that. The top being the bottom of the head. And that'll take up 30 thousandths worth of space. Inside the combustion chamber. And then when the combustion chamber is 30 thousandths smaller, as if I had shaved the head 30 thousandths, I'll go ahead and remeasure it again with the Burette, and that'll tell me how much reduction in cubic inch volume, I'm sorry, in cubic centimeter volume I obtained by having that much less water in it. Whatever thickness this is, doesn't matter. It's 30 thousandths, it's going to be 30 thousandths on the shims. Now this plastic shim stock is fairly non-compressible. It's pretty hard. It's made to hold its dimensions, and it's also a little brittle. So it won't be too easy to get it to mark here on the edges. So I'm going to take a pencil, color all the edges right on the edge. That's why I cleaned them up with brake cleaner. Hopefully this will work. And then when I tap that shim stock in there, not only will it get a little mark, a little line from the edge, and these edges are sharp, but it will be highlighted with a little bit of, hopefully, a little bit of graphite. If not, I'll have to try something else. There was a lot of loose graphite inside the chamber. I just blew away. Hopefully it stuck to the edge enough so it'll show. And so I'm going to experiment with some pink here. I don't want to ruin the little bit of brown that I have. Not even sure what size pink is, but it doesn't matter for what I'm doing right now. So that'll hold it in place so it doesn't move around. I can kind of see the mark showing through, so that's a good sign. Can you see the marks there? I won't know if the camera can see it until later. Alright, let's see what we have. You can certainly see that mark. Well, you can sure see that mark. Now I need to get a good sharp pair of scissors and I'll cut that out. By the way, this shim stock package is $45. Very expensive, so I don't want to waste any of the brown and yellow on the first try here. That's why I'm using pink. I don't want to have to buy any more. If I did, then I'd have coral and I wouldn't need the two of them. So the first thing I did is hog out all the wide edges. Now I can get down to the close cuts. Okay, so it's not exactly perfect, but it's very darn close. So I think this is going to work fine. You're probably still wondering what I'm going to do with this. Yeah, I mean, it's a tight fit over here, a little loose here, a little loose there, a little tighter over here. I think the imperfections kind of cancel each other out. So it's going to be close enough to prove what I need to prove. All right, let's get some more pencil lead on here. That was the practice run, which was pretty good. So it needs to be, the piece I'm working with, about 3.5 inches wide should do, and 4.5. This shim stock is 5 inches wide. can actually feel the marks here. Okay, next time I'm going to make the sheet a little bigger so the tape can be out of the combustion chamber area. Same over here. I don't want to be tapping on the tape. It makes it too difficult to see what's going on. This looks like I might have actually cut that shim with the hammer on the edge of the chamber. Yeah, right there. Yep. Yeah. Well, it's going to be a little easier to cut with the scissors with a good mark on it. That's almost perfect. See something here. Okay, I'll trim that. So that, I would say, I'm going to call it perfect. It's as close to perfect as I can get it. Perfect fit. The brown is only 10 thousandths thick and it feels a lot flimsier, and we'll see how this goes. I didn't put any of the pencil on it this time. I don't know how well that's going to show up on brown, but these marks show really good, so. What I'm seeing right now is that this shim is going to be cut out just by the hammer hitting it on the sharp edges of the combustion chamber. Interesting. Slightly rough edge, I can deburr that. But I mean, it was cut out by the chamber, so it has to be basically a perfect fit. Close. Just a little bit of deburring. This rounded part here is a little big. I'll clean that up on the deburring wheel and see how it fits. So this is almost a perfect fit as well. I really couldn't get it any better than that if I tried. Hi guys, after the last video I put out about CCing the cylinder heads, I actually finished CCing the other three combustion chambers on this head, and it turns out that, so I called this number 1 in that video, it was 65.8 cubic centimeters. Number 2 is actually, I measured it, 66.8 cubic centimeters. That's 0.8 of a cubic centimeter larger. Less than 1 cubic centimeter, but still, that seems like a lot. Number 3 is 66.2 cubic centimeters, still, you know, pretty big. And number 4 is 65.8, just like number 1. So I'm wondering if I shave the head 30 thousandths, what effect that'll have. And I did some compression calculations, compression ratio calculations. And I actually learned that 30 thousandths off the 4-inch diameter of the bore is a little over 6 cubic centimeters, but obviously the compression chamber is much smaller than the full 4-inch diameter. So 30 thousandths off the head will reduce the compression chamber volume by how much? So that's what I'm trying to learn in this video. So there's the 2 shims I made. You put them together, they're 30 thousandths thickness, which represents the 30 thousandths I want to shave off the head. Well, how am I going to use these, you're wondering? I can't just set them in there to take up space, even though they're the exact volume of 30 thousandths shaved off the head. These are the same cc's as the amount that would be shaved with 30 thousandths. So what I'm going to do, believe it or not, after all that trouble making them as perfect as I can, is I'm going to turn these basically into confetti. And all those little pieces of these shims, I'm going to lay inside the chamber with a tweezer one at a time when the chamber's half full, so that I know there's no air or anything stuck underneath them. And once those are all in there, the size of the chamber will be reduced by 30 thousandths. So that's the actual volume of the chamber being reduced, equivalent to a 30 thousandth shave. So I'm going to start filling it without the plexiglass plate on it. I have to put enough fluid in there so that all the little bits of this shim will be submerged. And then I'll put the plate on top of it and finish the test. I reset the fluid level inside the burette back to 0, which is the top. All right, maybe that's enough. So I don't know. Yeah, that's a problem. They float. Nope, I got it to sink. By putting them one little piece at a time on edge like that, That ensures that they're not going to have any air trapped underneath them. I have to make sure I don't get any drops of water spilled here off my tweezers. Okay, and I'll continue on with this. I don't see any reason to keep the camera rolling. I'll be back in a couple minutes. That one's floating. We don't want that floating. There we go. This can be out of the way. Here's the thing, if I take a few drops of water out of it, it will read a little higher than it should. So it's not going to give me a false sense of security that the chamber is that much smaller. Put enough grease around the edge to seal it, to seal the plate to it. That's one drop right there. Okay. Put my CCing plate on top there. And of course what I discovered is that it works better when it's clamped down, so I'm going to do that. That chamber's almost full. Let's get this burette in there. And we're ready to go. If I can get my hand in here. It's more difficult with the clamps in the way. Filling, filling, filling. Whoa. Well, a little extra water bubble came out there. I don't think there's any air in there, so just a tad more came out than should have. And this burette is reading. I can't see it, I need the light. The burette is reading 62.4. So that chamber is 66.6, and we just put in 62.4 or 3. There's just a little extra dab of water that came out, so maybe it's 3. That means that 30 thousandths worth of shims consumed 4.2 cubic centimeters of space. So that so-called 4 thousandths rule of thumb equals 1 cubic centimeter is completely wrong. Completely wrong. If I take 30 thousandths off this head, I can bring this particular chamber into spec, being between 60 and 63. It's about, well, it's 62.3. I just measured it with 30 thousandths taken off of it. So that's a little discouraging. So if I take 30 thousandths off the head, number 1 here will be 61.6, 2 will be 62.4, 3 will be 62 even, and 4 will be 61.6 cubic centimeters. The spec on these is 60 to 63. So they'll all be within that spec. The difference between the largest and the smallest, 62.4 minus 61.6 is 0.8. So now let me figure out what it would be if I took off 40 thousandths. Now we have a number that we can work with. If you take off 30 thousandths, you subtract 4.2 cubic centimeters from the volume. So if you shave the head 30 thousandths, it reduces the volume of the combustion chambers by 4.2 cubic centimeters, cc's. So if you take that 4.2 and divide it by 3, you get 1.4. So add that 1.4 to the 4.2, which would mean you took off 40 thousandths. It's 5.6. And then the cylinders would, or the combustion chambers would be, number 1 would be 60.2, and that's great actually. Number 2 would be 61, and number 3 would be 60.6, and number 4 would be 60.2. So number 2 is still the worst, but 61 isn't terrible. So I'm going to do some math on calculating the compression ratio next. The compression ratio is the ratio between the maximum and minimum volume during the compression stage of the power cycle in a piston engine. This diagram shows a piston in a cylinder at the bottom of its stroke. Like the Ford 289 engine, it has a stroke of 2.87 inches. That means the piston travels up and down 2.87 inches. The diameter of the cylinder is 4 inches, like Ford 289 and 302 engines. The 289 and 302 share the same piston dimensions. The cylinder head in red has a combustion chamber in it. By accident, I made this combustion chamber look almost hemispherical, like a Hemi head engine. When we're calculating the compression ratio, we add the cubic centimeter volume of the cylinder, the combustion chamber, the head gasket, and the piston to block that clearance to determine the total cylinder volume. This diagram shows the piston at the top of its stroke. Notice there's a head gasket pictured, and there's space on the top of the piston below the head gasket that represents the clearance between the piston and the top of the deck. For compression ratio calculations, the volume of the combustion chamber in cubic centimeters is added to the area of the deck clearance in cubic centimeters and the area of the head gasket in cubic centimeters. Also note that the head gasket has a larger hole diameter than the cylinder. The compression ratio is the ratio of the total cylinder volume to the total combustion chamber volume. We start with calculating the volume of a cylinder. This cylinder has the same diameter and height as the stroke of a Ford 289 engine. The example shown calculates the volume of the 289 cylinder. But then we have to calculate the volume of the cylinder hole in the head gasket, and the cylinder created between the top of the piston's travel and the top of the engine block deck. So there's 3 cylinders we have to calculate. The formula for the volume of a cylinder is V equals pi r squared h, where r is the radius of the cylinder wall diameter, h is the height of the cylinder, in this case the length of the stroke, and pi is the familiar 3.14159 value we're always applying to circles. The radius is half the diameter, so it's 2 inches. Let's plug our values in and calculate. V equals 3.14159 times 2 squared times 2.87 inches. We're doing these calculations in inches, but we'll convert the answers to cubic centimeters in the next step. The volume of the cylinder is 36.065 cubic inches. If we multiply that times 8 cylinders, it's 288.5 cubic inches, just under 289. Now I'm going to blow your mind a little bit by showing you a spreadsheet I developed to do all these calculations for me. So this is a Microsoft Excel spreadsheet. If you're not familiar with it, I'll just try to explain briefly a little bit about it. As I move my mouse around, you can see here, and I'm selecting these boxes and changing the width of the columns. These are columns. The columns are identified by alphabetical order here at the top, so that's column A, B, C, D, E, etc. And then rows are numerical, so there's row 1, 2, 3, 4, 5, etc. The number of rows and columns they're not unlimited, but they are absolutely huge. I mean, you're not going to run out. Right here I am down to row, just scrolling down here. You can see on the left hand side it's scrolling. I'm down to, this is row 50,798. So that's crazy. And if you do the same thing with the column header there, let's see. I'm getting back up to row 1 again. Columns. So columns start here with A, and then I'll just use the right arrow. There's B, C, D, E. I'm just holding it now. You see that? What it did? Well, after it hit A, it went to double A, double B, double. Went to AA, AB, AC, AD. And then it will go, after it hits AZ there, right here, it goes to BA. BB, and it just keeps going. C, D, E, F, G. Here I'm up to G, N. So there's more than enough space for anything you want to do for the most part, unless you're working with an industrial application. So what does Excel do? Well, you can create tables of information on sheets. So this is a sheet right here. This is one sheet, and if you look down here, there's 4 tabs, and I'll just click on, this is the sheet that we're on, and here it says chamber, CC, and shaves. So I'll click on that sheet, and I built a table with all the data in it from what I've read so far with the Burette. These are the CC readings. These are the CC readings here that I read. And then when I did the 30,000 shaved head experiment, that's those numbers there. And then these numbers were extrapolated from that with a 40,000 shave and a 50,000 shave. And I thought, well, what if I want a smaller shave? There's a 20,000 shave and a 10,000 shave. So if you did a 20,000 shave on this head that has a 66.6 cubic centimeter combustion chamber, and we said 20,000, that would be around 63.8 now cubic centimeters. So it's actually 3 cubic centimeters almost smaller at if you do a 20 thousandths shave. If you do a 10 thousandths shave, it would be 65.2. So there's a lot of useful information there while I'm trying to figure out the combination of shaving the head and maybe using pistons to get the compression ratio I want. So I'm going to click on the lower left here. You see the tab I'm clicking on, it says flat top pistons. Now this is where I did the calculations for compression ratio with flat top pistons. Here it says calculate volume of piston stroke, right there. And then there's that formula, V equals height times pi times r squared. Well, what's very useful with these spreadsheets is that these, see all these little boxes, they're called cells. You can put a little program behind the cell to do mathematical or logical operations. So for example, this one says radius squared 4. Well, let's step through this. How did the radius squared get to 4? The cylinder bore right here, you can see, is 4. That's what we've been using. But then the radius is that divided by 2. So it's 2. How did that get 2 in there? Did I just punch 2 in there? No, this has a little program in it. And it's right here. You can see it. It says L4 divided by 2. So L4, that's column L, the fourth cell down. So that value divided by 2 is 2. And then the radius squared will be that radius, which is an M4 squared. And so what we have in here is M4 times M4. You see that? And that's how the radius squared got to be 4 right there. Then if you look over here, here's our volume equals pi times the stroke in inches, 2.87 times the radius squared. And that shows that it's 36.065 cubic inches, just like we calculated before, but now the spreadsheet is doing it here in the background. But let me just show you something real quick. What if we changed the bore to 4.030? That's a 30 thousandths over bore. Well, did you see what happened? Automatically the radius squared became 4.060. And because of that, the radius squared over here became 4.060, and the cubic inches grew up to 36.608. All right, so now I'll put this back to 0, and we're back to 36.065. So that automatically changes the cubic inch volume of the cylinder when I change the size of the bore, any amount. Okay, but we said we need to work with cubic centimeters. So to convert to cubic centimeters, I have this here. This is really just a note. 1 inch equals 16.387 cubic centimeters right there. So then in the background here, in cell L7, you can see I have that cell equals D5 times D7. So what is that? D5, so here's D and 5. You see that? I highlighted them, they intersect at that value, 36.065 cubic inches. So it's taking that times D7, which is inches, cubic inches equals 1 cubic inch equals 16.387. So it's multiplying the cubic inches times 16.387 and coming up with 591 and 0.005 cubic centimeters right there. So the cylinder, 591.005 cubic centimeters. And you'll start to see how useful this is as I continue here. So now let's look at calculate the volume of the head gasket. Well, the formula is still the same. It's pi times the compressed gasket thickness times radius squared. Well, the gasket cylinder hole diameter is 4.106. It's 106 thousandths. I measured it. So that gets divided in half, so the radius is 2.053, and you square that and you get 4.2148. And that 4.2148 shows up here as 4.215. It's rounded. So the volume equals pi times 215 thousandths, and you end up with a volume of the hole in the head gasket being 0.62234. Look at that, cubic inches. And then we come down here, and that's just that hole in the head gasket. And you come down here to convert to cubic centimeters, and it comes out as 10.2 cubic centimeters. So what's behind that cell there? 10.2 is, it equals D12 times D7. So here we are. D12 is that number, the cubic inches. Looking at the cubic centimeters again, you're multiplying it times that, and you get 10.2 cubic centimeters. You don't even need to know how the spreadsheet works to be able to use it, but it's helpful. So now we're going to calculate the volume of the piston to deck clearance. And I'm just using as an example 50 thousandths. From what I've read, the 289 deck clearance is probably 16 thousandths. But I'm using 50 just for the example. I need to go out and measure my deck clearance so I know exactly what it's going to be. There's pi times the deck clearance times the radius squared is 4, and it comes out to 0.62832. That's cubic inches. And again, that's around 5/8 of a cubic inch. So that gets converted to cubic centimeters, and it's 10.3. So look at that. The head gasket and the space above the piston up to the deck, you're adding 20.5 cubic centimeters of space. That you're adding that actually to the combustion chamber, if you think about it. Then, let's see, down here I have the cylinder stroke plus the head gasket plus the deck to the piston plus the chamber. And that just takes all those values, that one, that one, that one, and the size of the chamber there that I plug in manually, and adds them up, and that's 671.1 cubic centimeters. And then here I have the gasket plus deck to piston plus chamber, so that is without the cylinder. In other words, the cylinders are already up at top dead center, and that volume is 80.9 cubic centimeters. And so the last thing that we're looking for here is the compression ratio, and that is H22, which is this, divided by H25, which is this. So you're dividing the combustion chamber into the total volume of the chamber with the compression chamber and gaskets and all that. And it comes out with 8.38 to 1. That's your compression ratio with a 59.6 cc combustion chamber volume. Well, that isn't too cool, but you want to see a really big difference here? You'll be amazed. If you change the deck clearance here to 15, look what happens to that deck clearance volume. It dropped from 10.3 to 3.909, and the resulting change in compression ratio, look at that, it went up to 9.1. That's a very respectable compression ratio, but that's with a 59.6 cc chamber. Let's look at our list. Where did that come from? Oh, that came from Crazy Town. If you shave 50 thousandths off the head. Let's see what it is if you're at what the head actually is now, 66.6 cubic centimeters. So I'll put that in here, 66.6, and that gives us a compression ratio of 8.4 to 1. So that's the true compression ratio if I'm using those heads with flat top pistons. And if the deck clearance is more than, oh, it was supposed to be 16. That makes it 8.38 to 1. But if the deck clearance is more than 16, make that 50. With that cylinder head the way it is now, it's 7.79 to 1 compression. And I'm honestly hoping I can get a lot more than that. Okay, I'm trying to find out if this is in top dead center. This is the #1 cylinder, the #1 piston. And I want it at top dead center because I want to measure the piston to deck clearance. I have the dial indicator touching the piston right now. I think it's at top dead center. Make a little adjustment here. Okay, it's basically at 0. So I'm going to turn the crank and we'll see what happens. There the piston is dropping away. And now I'll bring it back up. No, I can't. It'll have to go all the way around, I guess. Here it comes back up toward the top. All right. You can see it where it hits the top of its travel, and then the needle reverses direction. See that? So that right there that's the top. I'll drop it down a little. We'll come back up again. That's the top. That's reading at the 2,000ths mark on the dial indicator. Yep. When it's right on 2, it's at top dead center. And there it is. That's the most accurate way to find top dead center. Okay, so I'm going to very gently lift this off. I don't want to stress the indicator out at all if I can help it. And this is a magnetic base. So this is called a parallel in the machine shop. The sides are perfectly parallel, and so are the flats. They're ground on a precision grinder. So I'm going to use this. I cleaned off the surface here. I'm going to use this to bridge the piston because I don't have a depth mic. I'm going to just have to measure it the best way I can. That's with a dial caliper. This is a Starrett dial caliper. There's a clean spot on the piston right there. I'm just going to go ahead and plunge this down. And that's that. That's the best measurement I can do. It's reading 271 thousandths. And what's the thickness of the parallel? About 251 and a half, 252. So the clearance here is 20 thousandths. I'm going to use 20 thousandths deck clearance for my compression calculations. And that's awesome. Let me just do it again. There we go. 277. 277 again. And the thickness is 257. So it's 20 thousandths. That's great. That's a good number. Okay, let's consider our options though. I have another sheet down here. You see where I'm pointing with the mouse? So here's that deck clearance of 16. I now know I can change that to 20, and this is going to be a pretty accurate estimate of my compression ratio. So with a big dome piston, I'm talking about a domed piston now, that means I would be installing new pistons, so that would necessitate a 30 over bore at least. So I'm adding that in right from the beginning. So it's 4 inches and 30 thousandths. So the cylinder volume increased to 599.9. It's almost 600 cubic centimeters. Nothing changes here on the gasket thickness, and the gasket volume is still 10.2 cubic centimeters. Deck clearance now, that has changed, and the piston to deck clearance is 4.18 cubic centimeters, which is going to change some things. With the biggest chamber that I have, 66.6, that all winds up as 8.41 to 1 compression ratio. However, with the addition of domed pistons, and there are some Keith Black pistons that have a 14.7 cubic centimeter dome on them. Even with that big combustion chamber, those dome pistons result in a 10.27 to 1 compression ratio. Not too shabby. So what I've got is now a 30 over bore. The gasket thickness is still 47 thousandths. The deck clearance is confirmed to be 20 thousandths. You'll see 16 thousandths suggested a lot online, but 20 actually provides a greater volume, so that's to be on the safe side also. The cylinder stroke plus the gasket plus the deck to piston clearance plus the chamber is 680.88 cubic centimeters. I'm using the combustion chamber of 66.6 cubic centimeters, and the gasket plus deck to piston clearance and the chamber combines to be 80.98 cubic centimeters. Now, without the domed piston, that results in an 8.41 to 1 compression ratio, but with the domed piston, it's 10.27 to 1 compression ratio. You have to test with clay to make sure you have adequate clearance inside the combustion chamber, because that dome is protruding up inside the combustion chamber to take up that volume. It's taking up 14.7 cubic centimeters of volume. So you have to test that. You don't want the pistons colliding with the inside of the combustion chamber or with either of the valves. If you have a serious camshaft with high lift, there's a danger that the pistons and valves could collide. So you need to be careful with that. So there's a lot I have to consider and a lot of things I have to check out before I decide to buy dome pistons. There are pistons with smaller domes, like maybe 8 cc's, and they would give me a 9.33 to 1 compression ratio. With that big, this may be the way to go. I'll have to look into some different pistons, but they would give me a 9.33 to 1 compression ratio with that big combustion chamber. I honestly like the look of that, especially because if we go take the smallest chamber in that head, it's 65.8, and I still have to check all the other chambers on the other head, but 65.8 cubic centimeters, and that results in 10.39 to 1. This is actually quite a bit of compression. It would be really nice though, I gotta say. So that's something worth considering. Other than that, a smaller dome. I need to shop to see if there's really a smaller dome that's like maybe that. A -6 cc's dome. I think I saw something like that. And that would give us a lower compression ratio right there, 917. How about with the big chamber? 908 to 1. That would be a really civilized compression ratio, actually. Or use that piston, a piston with a 6 cc dome, and shave it 10 thousandths, shave the head 10 thousandths. That would be 65.2 cubic centimeters. Bring it to 923 to 1. That's very interesting, actually. And let's see, the smallest one in that case would be 64.4. $933 to 1. And that's if we're shaving the head 10 thousandths. What if we shave the head 20 thousandths? And I'll go here with 63.8 first. 63.8. That's very nice. 939 to 1. And 63 is the smallest one. 9.5 to 1. That would be worth considering as well. So what I need to do now is actually research what pistons are available and the size of the dome, and plug them in here, and plug in the different combustion chamber volumes depending on how much the head is shaved. And check out the interference fit, the interference possibly of the dome inside the combustion chamber or hitting the valves. But if I find a combination that works nicely, it gives me about 9.5 to 1 or 10 to 1 compression, that would be the way to go, especially if you don't have to shave the heads very much or at all. But I would have to get the block board 30 thousandths. It seems like a really nice amount. Shave it 20 thousandths. So that's interesting, and I need to investigate things and see what I come up with. Earlier on, I put a message up on the screen that said there was still something else to consider. So let's talk about that now. When I brought up the topic of dome pistons, I said that a dome on top of the piston will decrease the size of the combustion chamber and increase your compression ratio. But we haven't considered what happens when you have a flat top piston, which nobody really sells a flat top piston. In all my examples, when I didn't have a dome piston, I used a flat top piston, and we ended up with these numbers here. Like, for example, with the 66.6 cc combustion chamber, this ends up with 8.41 to 1 compression. But all the pistons I've been looking at are not flat top. They have valve reliefs cut in them, and some of them have dishes. They're dished. So we have to consider that. Now, a flat top piston like that is entered as a negative, and my interpretation of that is that it actually decreases the volume of the combustion chamber by that much. But if you have a dished piston, let's say you had a dish that was 6 cubic centimeters, that's going to increase the size of the combustion chamber and decrease your compression ratio like this. So if you had 6 cc's worth of valve relief in the top of the piston, we've been saying that's 8.41 to 1 compression, but if you account for that 6 cc's, it's really 7.83 to 1. Now I've actually seen a piston that's 6.64 cubic centimeters of dish. And so that would take our compression ratio from 8.41 down to 7.77 to 1. Okay, I've seen a piston that has valve reliefs that total 8 cubic centimeters. So that would bring it down to 7.65 to 1. The most extreme example I've seen had a dish in it that was 22 cubic centimeters. So that would bring the compression down to 6.61 to 1. When you're doing your compression calculations, you need to consider negative cubic centimeters on your compression chamber if you have a dome. So like a -6 would be a 6 cubic centimeter dome on top of the piston. And that would increase your compression. A positive value here would be a large valve relief or a dish in the piston that decreases that actually increases the size of your combustion chamber. So it decreases your compression ratio. So that's what I was referring to when I said there's more to consider than what we had already considered up to that point. First step, calculate the volumes of the cylinder, deck clearance, head gasket hole, and combustion chamber. You'll need to use the formula for volume of a cylinder 3 times, and you need to know the most accurate number you can get for the combustion chamber volume. CCing combustion chambers is the best you can do with that. The gasket manufacturer, in my case Velpro, provides the cylinder hole diameter and compressed gasket thickness to use in the calculation of the cylinder formed by the head gasket hole. Next step, convert the calculated volumes to a common unit. For example, cc's. You can use cubic inches, but cc's are smaller units, so they provide greater resolution. I used cc's in all the examples in this video. Now add up the volumes of the cylinder plus the deck clearance plus the head gasket hole plus the combustion chamber. Next, add up the volumes of the deck clearance plus the head gasket hole plus the combustion chamber. Divide the total volume by the volume without the cylinder. This example equals 8.333 to 1 compression ratio. Here's my GT-40 head data table with the second head data added. The variance on head number 2 is 1.4 cc's across the 4 combustion chambers. I'd say this head is a little better balanced than the first head. Stay tuned to see what I end up doing with the heads and pistons in this engine to get the compression ratio I want. Thank you for watching. Please take a moment to like and subscribe.